Just say the voltage in this thing. 6 times 2. Just say voltage in this. You're saying, like,
All right, for this one, what is this, mesh node? Which one? 7. Okay, you want the voltage here, is that right? Is that what we want, class? Yes? Is that what, the middle one, they want the voltage, right? All right, so what does Stevenin theorem say? First thing, what do? Identify the load. In other words, the element that you want some information about, and that's pretty obvious. It's 2K, right? So our load is just 2K ohms. Do we agree with that? What's the next thing you do? Remove it, right? So now I remove it. Agreed? Now what do? We find 2 things. First, we need the V open circuit, which is often referred to as V Thevenin, right? The open circuit voltage there. Do you all follow me on this? Right? How do we calculate it? And I don't care how you do it. It's pretty simple when you got one complete loop. Do you all agree with that? Let me just show you here. You all see current can only flow this way? Can you see that? There's no other option. If it can only flow that way, and you want this voltage from here to here, let's say we get the current first. How many agree with that? Sure. And if you take a look at this, I'll start at this point. So if I start at the lower left-hand corner and I go around, I go from here to here, or a increase of 12 volts, then I get minus what? 1K times I, agree class? And then I just I in this case, minus 1K times I, right? Keep going, so now minus again. What about this? It went from a lower to a higher, so it's an increase. Plus 6 all equals 0. Is that right, class? Most of you can see through this, but I'm doing it for a reason this way. So if there's any doubt, you'll clear it up here. Everybody see what I've done? Now, by this time you can see the 1K and 1K times I become 2K times I. Does everybody agree with that? So I'm just going to make it minus 2K times I. That's the equation. And what about 6 and 12? 18, correct? Everybody agree with that?
Yes.
Can you all see it in the back too? I want to make sure. If you can't, yell at me, don't worry. I take no offense. So now it makes 18. Finally, I can take the minus 2K on that side if I want, divide by 2K, it doesn't matter how I do this. At this point, I know that 18 over 2K ohms would be equal to I, or it's really equal to what? 9 milliamps. Do you agree with me, everyone? Everybody? I know I'm going this in a way that's kind of slow and boring, but it will help people, trust me. Now, next thing I'm going to do is just assign the voltages. That means right here I have 1K times 9 milliamps, or 9 volts. Correct, everyone? Can everybody see this? Does this make sense? I'm just multiplying current times voltage. I calculate the current. Here, I also have 9 volts, correct? Everybody? Now, I want to find the open circuit voltage. So, V open circuit here, or V Thevenin, would be equal to, I told you before, start at the negative terminal, right? Didn't I? This is the way I do it. Start at the negative, get to the positive. To get to the positive, I get an increase of 12, don't I? Y'all see that? And a decrease of 9. So this is equal to 12 minus 9. We could have gone this way. Do you all agree? So if we go this way, what do we get? A decrease of 6 and a increase of 9. You all agree with that? And that is what? 3 volts, no matter which way you go. Do you all see? It's path independent. If you go from the negative to the positive terminal, it doesn't matter what path you take to get there. However many voltage increases or drops you go through, they'll add up to the same thing. Got it? Now, that's the open circuit voltage right there. That's 3 volts. The third thing we do is find R Thevenin, right? Agree? Now, what do we do to find R Thevenin again? We turn off the sources, don't we? And if we turn off the sources, voltage sources become short circuits or wires, right? They become wires, so this becomes a wire. And this becomes a wire. Right? You ask this, you ask this. Do you see what I'm doing? Everybody clear on this? Now we need to find the resistance between those 2 terminals. I want you to take a look at this if you haven't already. The resistance between these 2 points, right? Can you see that these 2 are in parallel with each other? How many see that? They have the exact same voltage across it, don't they? In matter of fact, the way I told you, if you took a marker with a certain color, I'm using blue, you get that. Then if you took a different color, red, starting here, everything between the the blue and the green would have the same potential, same voltage, right? And therefore they would be in parallel. Now, how many see this right here? All right, good. So I have 1K in parallel with 1K. And that's really what? Remember what I told you about resistors in parallel? You take the value of any one of them, if they're all the same, and just divide by the total number, right? We got 2 resistors of 1,000 ohms in parallel. So we divide by 2 or 500 ohms. How many see this right here? Right? Y'all with me on this? This is very simple. So that means R Thevenin is just 1K in parallel with 1K, or it's 500 ohms, or 0.5 k ohms, right? Can everybody see what I'm doing? Are there any questions? If there are, please ask them. There's no stupid question. And I never laugh at people who don't understand, because half the time the writing's where they don't understand. Yeah?
I couldn't understand.
The writing?
Yeah,
R Thevenin is 1K in parallel with 1K. That symbol there is in parallel. All right? It means 1,000. Here's what it really means. If you want the equation, it's 1 over R1 plus 1 over R2, or it's equal to R2 R1 over R1 plus R2. Since they're identical, 1 over 1,000 plus 1 over 1,000 is 2 over 1,000. Flip it upstairs, 1,000 by 2 is 500. Everybody got that, everyone? If you can't read my writing, let me know. I'll try to interpret it. So that's R Thevenin. Now you build the circuit. When you build the circuit, you put the open circuit voltage, VOC here, which happens to be 3 volts. Then you put R Thevenin here. R Thevenin is 500 ohms. And then that's where the open was, right? Now I'm going to label this. This was the plus. That was the minus terminal. This will be the plus. This is the minus. And now you replace the load. You put it back in. And the load was 2K. Do you agree, class? 2,000 ohms. Does everybody agree with that? Yes, sir.
You said that those 2 at the top were in series?
No. When we were doing the first part of the problem and we had voltage sources, they were in series, weren't they?
Yes, sir.
But the second part is determining the resistance between these 2 terminals when they become short circuits, right?
Yeah.
Then they become in parallel, don't they?
And the 2 up top do?
Well, they have to. Remember I said everything between the green and the blue have the same voltage, don't they? Because just think, if that's plus to minus, plus would be here, minus would be here, you see that that voltage is directly across them. What I tell people sometimes is just take them and bend them down, and they look more parallel. Follow me on that? Got it? All right. Now, finally, what's this voltage? Because this is what they were they after the voltage of the current? I don't know. Why don't we get both? What is the voltage right here across that 2,000 ohms? Anyone? You can do it a couple of ways. How would you get it? I got 3 volts there, and I want that voltage. How many know what voltage division is? Show of hands. Couldn't we use voltage division, right? Take the source voltage, 3 volts, then multiply it by the element you want the voltage across, and divide it by the sum of the 2 resistors in series causing that division, which would be 2500, right? So that's what? 6 over 2.5, isn't it, class? You could say that V2000 was 6 over 2.5, right? And any other form you want. Do y'all follow me on this? What's another way you could do it just briefly? Well, couldn't I calculate, whoever said that's right, I could find the current, right? The current would be 3 over 2500. Do you all see that? And then if I multiply it by the 2000 ohms, I get the voltage, correct? Did they ask for current or voltage? All right, so for current, that I, it's straightforward. It's going to be 3 divided by 2500, right? You agree with that? Amps. Follow me? That's it. That's it. Another question. I'm trying to dispel any confusion. Remember, we did nodal. First, we did summing resistors in series and parallel, adding voltages in series, right? Current sources in parallel. We did source transforms. We did nodal. We did mesh. We did Thevenin. We did Norton. Right? Those are our analysis methods. They all get us to the same place. I'll ask you specifically to do it in one way or another, all right? And you have to do it that way. But they're all just techniques to solve circuits problems. Some are more advantageous at times than others. That's the reason you get these. And that way you have a full toolbox. Any other questions about homework? Yes, sir. 3.63? 2.63. 2.63. And I'm sorry I don't have my book. Right back. I think it got lost in the shuffle upstairs when I was running around. Thank you. Here. Sorry. That's it's thicker than what I have. What does it say? All right. 2.63. 63. We should do this with a couple different ways just to show you. This one has 2K ohm. Then it has a source here of 2 milliamps. Then it has a resistor of 2K ohms. Then it has 4K. Then it has 4 milliamps. Now let's hear for a second. Is that all right? Just leave it there. All right, we're doing this problem, so remind me to throw these markers out. When we're doing this problem, did they want the voltage or what did they want? Current here, right? And they want us to use what method? Superposition? Did you say superposition, sir? Thevenin. Thevenin. All right, it won't matter what method. So if we're going to use Thevenin for this one, again, the first thing is identify the load. Therefore, RL is, class? I hope you can read it. 4K ohm. 4,000 ohms. Next, remove it. So then you erase it. Then you just do this. Plus the minus, that's V open circuit or V Thevenin. Do y'all agree with me here? I just remove it and I put in 2 little dangling ends. Put the plus on top, minus on the bottom. That's what I do. Now I want that voltage. So here's the thing. You can analyze this any way you want. I'm gonna show you a trick, and in my opinion, it's the easiest. When I look at this, just look. When I look at this, first see about the currents. Now, do y'all agree that 4 milliamp has to flow that way? Does everybody agree? Because it can't flow this way. It's an open circuit, right? If 4 milliamps is flowing there, do you see this voltage right here is 4 milliamps, 2K is 8 volts. Do we all agree with that? Give me a show of hands there, let me see that. It's by virtue of the fact the current can't flow any other way, correct? Now keep watching. This is how simple this one is. Now, if 4 milliamp is flowing this way and 2 milliamp is flowing this way, how much is flowing this way? 6 milliamps. Right? There's no question about that, right? Now, 6 milliamps is flowing this way. What's the voltage here? 12 volts. Do you agree, everyone? Now, if we have that, and we want the voltage, the open circuit, remember you can't go through a current source because you don't know the voltage crossing. Remember that. I start the negative terminal. I can't go that way as a current source. Go this way, can't go that way. I get an increase of 12, correct? And then I get an increase of 8. How many see that? I get 20 volts. So I get the open circuit. And I'm going to say something. A lot of times, until you do dozens of problems, it just doesn't snap off the page, all right? It doesn't. But anytime you see a current, always look for the voltages you can get with that current, always. Usually the problem just, reduces to nothing after that point. Because current sources tell you it doesn't matter what's ahead of me. I'm flowing through it, period. Got me on that class if they're in series? It's a gimme. Now, after that, the third thing is we have to find our Thevenin, right? To do our Thevenin, our rules say what? We turn off the sources, right? Voltage sources become short circuits or wires. Current sources become open. And the way I always do it to make the point, I erase them. Now they're not there. Correct? Got me on this, everyone? Whoever asked it, I hope this is answering your questions. Now I need to find R Thevenin. Let me get rid of the unnecessary information. I'm looking at the resistance between these two terminals, correct? By inspection, can you see it's 4K? How many see it's 4,000 ohms, 4K? Can you all see it in the back there? Guys, I'm really concerned sometimes because I see, the very back row. I don't care if you're texting, I just want to make sure you see this right here. If you got that, that's 4K. Agree? Now we build the circuit, correct class? We build the equivalent circuit. One voltage source, one R Thevenin. So we start with the voltage source, that's V open circuit, which is 20 volts, right? Then we add on the series R Thevenin right here, right? And our Thevenin is 4K. Then there's our dangling things. There's the plus and minus. Now we can put anything across there, right? Well, you can reduce, this is what's nice. Suppose I give you on some test because I'm in a bad mood. I'm going to say, what's the current for 4 different resistors? I want you to go and find it. Well, the way you do is put the Thevenin circuit, wouldn't you, class? And then quickly figure out a simple equation where that current would just be source voltage over R Thevenin plus your R for that current. Follow me? And you could just bang, bang, bang it. But if you had to solve it with mesh over and over again, you'd go out of your mind.
So which model is this?
63, isn't it? 63?
Yeah.
All right, so this one says the load was, did I leave it at 4K? So I put it back in. And you said they wanted the current, is that right? Or voltage? Current. All right, what's the current? 20 volts divided by 8K. Okay? Amps. And that's going to be what? Milliamps. So it's 20 over 8. 10 over 4, 2.5 milliamps. Y'all agree with that? All right, remember, everything's fair game. Any other questions about prior to hope? Yes, sir.
Could you do this same one by superposition?
Okay. Help me out here. This was 2K down here, wasn't it?
2K.
And this current was 2 milliamp?
Yes.
And this was 2K, is that right? 2K, and this current was 4, is that right?
Yeah. There's another 4K resistor.
Over here?
After the, in between the,
Here?
yeah, right there.
4K? All right, and they want this current, right? Is that right? All right, well, he asked me about superposition, so I'm going to be very clear about that. Superposition says you turn off, you've got two sources, you turn off one of them, analyze the problem with that source off, find the output. Then you record that output. Then you turn on the other source, turn off the first source, and find the output. Then you add the outputs together, that's superposition, right? It's based on linear systems, and this is a linear system. So for this one, my output is this, right? Agreed? I'll just call it I naught. And I'm gonna have I naught due to this source, and then I naught due to that source. Follow me? So, hear me now, who asked this? All right, follow me on this. I'm gonna first call this source 1 and this source 2. So for source 1, that means the 4 milliamp is off, right? I'm gonna do this by erasing that, because when it's off, current sources become open circuits, right? Now, I wanna find the current flowing through here, agreed? I'm gonna redraw it right here. You see how that looks like 2K here, 2 milliamp here, and then you have a sum of 2K and 4K in series, or 6K, correct, class? Or 6K in series. And what I want is this current, right? That's I naught from the first source. Y'all see that? Show of hands here, y'all got it? Now that's perfect current division, isn't it? Two resistors in parallel with a current going into the node. So I can say for this first source, my I out from source 1 is just going to be the source current, 2 milliamps, then it's times the opposite resistance, 2K, over the sum of the 6 and the 2, or 8K, right? So that's going to be equal to what? I have 4 milliamps times K, 4 over 8K is going to be 1/2, right? Milliamp. Do you all agree with me there, class? Everybody? Give me a show of hands here to make sure, right? That's the first one. Now I know I'm taking liberty with my erasure. Yes, sir.
So how did you get the 2 over 8?
Remember what current division says. It says if you have current going into a parallel combination, you have to see that these two are in parallel, right? And you want the current through a resistor. It says you take the total current and you multiply it by the opposite resistance, and then divide by the sum of the two resistances. Correct? You got me on that, everyone? You could find what a parallel value of these resistance, right? And then multiply by the current, then you have a voltage. Do you agree with me? And then you could take that voltage and divide by 6K, and you get the same thing. But anyway, that's 1/2 milliamp. Now, the second part is again, now I turn on this source, and that was 4 milliamps. Thank you. 4 milliamps. And I turn off this source, right? And now I get I naught. Correct, class? Now, what do you see here? Becomes an easier problem. How many see that the 2K and 2K are in series? Show of hands. Can you see that? By this time, you probably, it's just jumping off the page. Engineers see these things instantly almost. That's 4K. What do you notice about this? Two resistors in parallel. one current going into it. Don't you think about half of the current will go one and half to another instinctively? Sure, but you can prove it, right? You can say that that current I naught for the second source would be this 4 milliamps here. Opposite resistance 4K over the sum of 4K plus 4K or 8K, that's just equal to 2 milliamps. Correct, class? Do we agree? Now, what is the output going to be? Well, it's the first current plus the second current, right? Using superposition. So A out total would be equal to 1/2 plus 2 milliamps, or 2.5 milliamps. And I think that's what we got last time. Is it not, class? Everybody got that? Any other questions regarding this problem? Yes, sir.
Can we solve it using source transformation?
We can do it every which way you want. I'm up for it. We'll do it, how about we do it in mesh too while we're at it. Might as well throw in a nodal just to. All right, he asked about source transforms. So I'm going to do source transform. Bear with me. This is 2 milliamps. This is going to be a trivial problem, source transform. It's going to go this fast. Now, listen to me, all right, people. Source transforms say one thing. When you do a source transform, you don't transform the element you want the information about, either voltage or current. You leave that alone. Got me? Now, take a look at this for a second. 2 and 4 milliamps. Aren't they both going to the same node right here? Can you all see that? Without, you remember with source transforms, you add the current sources, you add in parallel the voltage sources in series. Remember when we keep reducing the elements? Everybody hear me on that? You all see that that 2 and that 4 are in parallel, correct? I can replace them with 1. I'm just going to get rid of this one and make this 6 milliamps. I added them together. Same exact thing, isn't it, class? Right? Now, yes.
The left resistor was supposed to be 2, and there was supposed to be a 2K in between.
What?
The leftmost resistor was supposed to be a 2.
Oh, this is 2K, sorry.
And then there was supposed to be a resistor in between the middle 2.
Right here? Wait. Tell you what, let me redraw the whole thing because I think I messed that up. Let's do this. There's a current here, I'll get that. There's a resistor here, right? Is there a resistor here?
Yes.
Thank you, I'm sorry I didn't get that one. And this is 2 milliamps, is that right?
Yes.
All right, and that is 4K, is that right?
Yes.
And that's 2K?
Yeah.
And that's 4K, is that right, class?
No, 2K. 2K.
2K here? Sorry. My bad. Now look, they want the current here, right? Isn't that right? All right, source transforms, pay attention to this just so you don't mess it up. We don't transform that. We transform everything else, right? Correct?
One on the right should be 4.
What?
On the right should be 4.
Pardon me, you're right. Thank you. 4 million. All right, now, one thing I'm going to tell you about this one. This is going to be, if with source transform is a bit odd, but I'm going to start on this side. Just listen to me. You're going to see how quick this problem falls apart. Remember, we don't transform that. Got me? When I take this in parallel with this, can't I replace that with a voltage source in series with that resistance, right? So I'd have 2 milliamps, 2K, that's 4 volts, right? In series with 2K. So I have 4 volts in series with 2K, right? Agree? Everybody with me? Now, that's 2K in series with 2K is 4K, correct? You agree with me? So now I replace, make that a straight line, and put that 4K. Everybody agree with that? Remember, with the source transform, you're reducing the number of elements by 1 every time. Maybe more than 1 at times. Agreed, everyone? Now, the next thing we do is what? We go back and make this a current in parallel with a voltage, correct? I mean, a current in parallel with a resistor. So when I take 4 volts by 4K, I get 1 milliamp, correct? In parallel with 4K, you all see that? So now I get 1 milliamp. And it's in parallel with 4K, correct? Agreed? I want to stop there. I want everybody to take a good look at it, convince yourself. It's important you're convinced that there's no uncertainty about what I'm doing. Now, you all see that this 4 milliamps and this 1 milliamp are both going into the same node right here. And they're flowing. You all see that? How many do? You see we can combine the count. So I can take this 1 milliamp and add it to that 4 and make it 5 if I want. Agreed? And oddly enough, we've hit, you know, the trifecta. If you have 5 milliamps flowing into the parallel combination of 4K, how much flows through each one? Half, right? Or 2.5 milliamps. Correct, class? How many see that? It's pretty straightforward. So I would be equal to 2.5 milliamps. Agreed? I'm trying to test this problem. But everybody got that? All right, now we'll do it one more time, just because we want to be sure. I'm serious. Why not do it with everybody? What's the yeah?
Going down instead of up.
What? Say
If the current was going down, the current on the left side of the 1 milliamp was going down, that turned into 4.
Let me just try to make you aware of one thing. Suppose I have a current source, 4 milliamps here, a resistor here, say 4K, and then I have a current here, but it's going this way, and it's say 2 milliamps going this way. You follow what I've done? This, I hope, is going to answer your question. Now, when you look at the top node, the node is someplace with beacon potential here. You see that I have 4 milliamps coming in, right? I have 2 milliamps coming out, right? The net effect is having 2 milliamps going up. Do you all agree with me? So what I can do is just erase this and make that 2. Now, I hope I'm answering your question. That's how you add them if they're in opposite directions. You take the larger arrow, leave it alone, and subtract the smaller number from it. All right? And just leave it in that direction. Agreed? All right. Now, last thing is going to be do this one. What did we say? No, loop. Mesh, right? Yeah, we could do it normal too, but it's almost a waste of time because it's one voltage. All right, help me out again. On the far left, it was 4K? Is that 2K. 2K. Here?
Down.
Huh? Current.
2 milliamps.
Keep going.
2K.
2K up top, 4K going down.
Go ahead.
4 milliamps on the outside. Going up.
Agreed, everyone? Now, this is one of these problems. It becomes almost trivial at this point. I'm going to show you what I mean. I'm going to call this I1. Got me? I'm going to call this I2. Follow me on this. I've got to choose a direction, right? And I go clockwise, unless there's an overwhelming reason not to, which there is in this one. You know why? That's already going the wrong way, let's say. Isn't it, class? So if the current is already known and designated in that direction, just leave it go in that direction. It's okay, all right? Follow me on that, everyone? Now you go and write the equations for voltage drops. I start right here, and I want you to notice one other thing though. When I look at this one, I have 2 milliamps going up, right? But what do I see when I have 2 milliamps, right, going up? That would be I2 minus I1. I want to make sure I make myself clear. You see there's a net 2 milliamps flowing up there. That's the definition, right? Well, what is that equal to? Well, how much current's going up? It's I2, isn't it? In this subloop, or submesh. How much current's going down? I1. So I2 minus I1 must be 2 milliamps. How many see that right there? And if you're in aerospace or mechanical engineering or some other variant of that, you understand that this is fluid flow. essentially, right? Basically, you have two fluids, one's flowing a certain rate, the other's flowing the opposite direction at a certain rate. To get the net total fluid rate flow in one direction, you'd subtract it. Follow me on this? Yes, sir.
On the last example we did, why do you have to put them in parallel?
No, they ended up in parallel. We didn't put them there. We had two current sources in parallel. And the young man asked the question about, well, what if one's in the opposite direction? What happens? And I said the net effect is subtracting that one from the larger of the two. Now, this is what we got. So now when we look at this, I want to show you something. We've already got one equation, don't we? Right? Please watch this. In this one, you can't go around this loop. Why can't I sum voltages around that loop? Anyone?
There's a current source.
There's a current source, right? Can I sum voltages around this loop? No, there's a current source, right? Can I sum voltages around this loop? Current source. What's the only way to get a voltage sum around basically around an entire loop without bumping into a current source? Y'all see that, class? How many do? All right, now with that in mind, let's do just that. There's our first equation. Our second equation is this. Start at the left-hand corner, all right? I've got a resistor 2K, so it's minus 2K times my I1, whatever I1 is. Then it's going to be minus 2K times what? Can you all read that? That's I2, isn't it, class? I2. Then it's going to be what? Minus 4K, keep going. I2, say it again. Plus 4 milliamps, very good. You all see that? Because now, these two, I chose it that way because it was what? Already defined for me in that direction, correct, class? Now they add together, don't they? Y'all see it? In the back there, good? Now that's the equation, that all equals 0. I'm running out of time here, but y'all see for this one and this one, we have two unknowns, two equations we can solve. How many see that? If y'all see that, you probably feel good that you're going to get this right answer for current and voltage, because we did for the last 3 ways, right? And you will, in fact. Y'all got me on that, class? All right, zoom in and